Alright, so welcome to the last data reduction video for the entire semester.
It's the thrill of one more kill, the last one to fall. Who never sacrifice their will. Don't ever look back on the world closing in. Beyond the attack with your wings on the wind. All the things will begin, and it's sweet. Sweet victory, yeah. It's ours for the taking. It's ours for the fight. It's sweet, 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 sweet victory, yeah. And the war is ours to fall.
Today we're going to go over the double pipe heat exchanger. So hopefully this goes by pretty fast and then you'll be done with most likely the entire semester for all of your classes. I bet there's going to be a select few of you that work on the data reduction before your finals, and that's good, but I'm sure most of you will be doing this towards the end, and that's fine as well. So anyways, let's go to the data reduction, what we have to do. For the first two deliverables here, we need to basically plot our temperature versus the axial position. So for number one, this is going to be for uninsulated, that kind of configuration. And then number two, this is going to be for the insulated configuration. So this right here, that should say insulated. So what we have is thermocouples 1 through 9, that's going to be for the hot fluid, and thermocouples 11 through 19, that's for the cold fluid. So in the lab, those thermocouples recorded in Fahrenheit, so we need to convert that to Kelvin. So we have the conversion formula right here, and we're going to do this plot for each increase in our flow rate. So what we have here is uninsulated parallel flow at 10 gallons per hour. That's for the hot fluid, and it's going to stay at 10 gallons per hour throughout the entire experiment. And then 2.5 gallons per hour, that's going to be for the cold fluid, and then we increase that for each run by 2.5 gallons per hour. So we have parallel flow on the left side here, and then counterflow on the right side here. We're going to plot all of these different runs on the same graph. So we're going to have 8 different figures basically, but it's going to be on one, really large, you kind of think of it as a page. So we're going to be using the subplot command in Matlab. Okay, number 2, it's the same exact thing as number 1 up here, but we're doing it for the insulated configuration. And number 3, we're going to plot our heat transfer versus our cold flow rate here. Okay, so we're going to do that. Make sure you read through all of this. I don't want to make this video too long, but read through it so you really understand the details of each part. And then for number 4, we're going to plot the overall heat transfer coefficient U versus our cold flow rate once again. And we're going to be doing that for parallel and counterflow configurations. That's for both number 3 up here and number 4 down here. Okay. And again, make sure you read through everything down here. And the diameter of our tube is given here, and the total length of the heat exchanger is also given here. Typically that's given in here Yeah, typically, I think here, I don't know. It's usually given before, oh yeah, right here. But it's not given here. This looks like it's from the last lab, at least for this part here. This is for the cross-flow heat exchanger. Yeah, you can see we have stuff for copper, so. Anyways, that's a little bit weird, I guess, but we'll make do. So let's go to Matlab. Add my graphs open here. Alright, so right now, all I've done, let me clear this all out. Okay, so right now, all I've done is, like usual, have our experiment here. I'm clearing the memory, specifying some constants. We have the water density, the specific heat for water, and then I'm going to define an array here for the volumetric flow rate. That's in gallons per hour, so this is for the cold fluid, remember, but we can also use this array for the hot fluid, because we're just going to use that at 10 gallons per hour. But anyways, we have 2.5, 5, 7.5, and 10 gallons per hour. The pipe diameter, and then the length, as I talked about, that was given at the end here. And then some conversion factors. We want to convert gallons per hour to cubic meters per second, and then inches to meters. And then we're going to actually convert some of our parameters here. So we have the diameter, the length, and then our heat transfer area, which is really just the surface area of our pipe. Pi times the diameter times the length. Okay, and then we're going to import and sort some of our raw data. So I'm going to import the file, just experiment 6 raw data. And then T range, this is going to be our temperature range that we have. So I did A4 to I21. So it's all of this data that we have here, and it's, you know, the same thing for each sheet, or the uninsulated and then insulated data that we have. Okay, so now what we're going to do is sort our raw data into separate arrays. So for this first part here, I'm just doing X position is going to be our data on sheet A. And then I'm going to take all of this and then I'll convert it to meter. So I'm just doing the axial position basically. So we're doing rows 1 through 9 and column 1. So I just need to do this part because all of this right here, that's the same. Because we're just doing the axial position. We have two fluids. We have a hot fluid and a cold fluid. So all of this right here, this is our hot fluid. So we're starting at a hot temperature and then we're cooling down. I grabbed too much, like this, okay? And then all of this data right here, this is for the cold fluid, where we're starting at a cold temperature and then we're going to heat up. Okay, so that's the axial position. And then what I have here is I'm converting all of our temperature data to Kelvin. So I'm just using that formula that we talked about earlier, right here. And then I'm taking all that data, plugging it into our formula, so I'm converting all of this to Kelvin. So I'm also really converting this to Kelvin, so you could exclude that if you wanted, really. And here I just forgot to do that, but we're not going to take that column anyway, so it'll be fine. Okay, and then all of this right here, we're just separating, again, the temperature data that we have into their own different arrays. So I'll talk about, maybe the first two here. So I have the temperature data for the uninsulated configuration, so that's TU, and then P, that's going to be for the parallel flow, and then H, that's going to be for the hot fluid. So uninsulated, so we're in sheet A, and then we're doing this for parallel flow, so we need to make sure that we're staying within this range here, and then we're doing it for the hot fluid. So basically what we're doing is rows 1 through 9, so here, and then we're doing columns 2 through 5, so right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 rows, and then columns 2, 3, 4, 5. So we're getting all of that data. And then if we look at the second one, we're just getting all of this data right here. So uninsulated, counterflow, and then the hot fluid. So we're going to do that for all of the other temperature arrays that we need to get. Okay, so now we're on the data processing portion. So for questions 1 and 2, there's nothing to really go over for that because all we have to do is plot the data that we have. We're going to plot all of our temperature data that we have up here, and then we have the axial position. So there's nothing to go over for that. Okay, so we could go to question 3. This is going to be for our uninsulated configuration that we had. So we're going to plot Q dot versus our volumetric flow rate for the cold fluid. So the equation that we're going to use here is equation 2.13. So our heat transfer, that's going to be equal to our mass flow rate multiplied by the specific heat for the water, and then T1 minus T2. So we have our specific heat, and we have the density of our water. We're going to multiply that by our volumetric flow rate, and then these two, that's going to give us our mass flow rate. Then we have T1 minus T2. So let's talk about this configuration here for a second. Okay, so for question 3, right here we have for uninsulated, and then let's look at these two lines. So we're looking at the hot fluid for parallel and then counterflow. So we need to remember how we have T1 and T2 kind of set up for us. So let's start at the parallel flow. So for T1 for the hot fluid, that's going to be T hot. Then T2, that's going to be as the hot fluid gets colder. So if we look here, we're starting at T1, that's hot, and then we're cooling down a little bit. Now for the counterflow, again, we're starting at T1. For the hot fluid, that's at a hot temperature, and then we're going to cool down a bit. So we're starting hot, and then we're cooling down a bit. Now for the cold fluid, let's go to parallel flow. At T1, it's cold, and then we're going to heat up. So parallel flow, cold, we're cold, and then we're heating up. Now for counterflow, and this is where it's different. So T1 for the cold fluid, that's its outlet temperature. So that's where it should have gained heat. So T1 for the cold fluid, it's heated up from our inlet, which is at this station 2. So that part can be a little confusing, but if we look here, we have T1. That's at a hotter temperature than T2 here. So just kind of keep that in mind. I know it's a little weird, but you know, it is what it is. That's the convention that we have to use. Okay, so we have all of that. And then we can move on now. Okay, so now we're going to look at our basically delta Q. So let's go back to the lab handout. We'll go to the data reduction. So it says to calculate delta Q dot equals Q dot H minus Q dot C. So for that, we're doing delta Q dot for the parallel flow, and delta Q dot for the counterflow, and then the U, that's for uninsulated. So we're doing for parallel flow here, we basically have QH minus QC. And then for our counterflow, we have QH minus QC. Okay, so that's it for question 3. Okay, so now we're on question 4. We're on the insulated configuration. So we need to calculate Q dot H and Q dot C, just like we did for the uninsulated trial. And then from that, we're going to find the overall heat transfer coefficient U. So we're going to do this for both parallel and counterflow. And then we're going to plot that against the volumetric flow rate for the cold fluid. And then take note here, when we calculate U, we need to use the heat transfer for the hot fluid, okay? Let's go back to Matlab. And before we get started, I should have also touched on this, where I have, where I'm multiplying our conversion from gallons per hour to cubic meters per second. When I multiply it by our volumetric flow rate for the cold fluid, or really the volumetric flow rate. Here for the hot fluid, I'm doing Q of 4, because again, for the hot fluid, we just want to use 10 gallons per hour. That's all we had. But for the cold fluid, we had 2.5, 5, 7.5, and 10 gallons per hour throughout. So for that, we're going to use some matrix multiplication here. Okay, so now for question 4, the first part we're calculating Q.H and Q.C. So that's all in this part. It's the same logic that we applied up here. This should be 1 minus 9. Okay, so it's that same logic that we applied up here. And then in this code here, this is del T1 and del T2. So for that, it's just basically I'm looking at our temperature differential that we have at our stations here. So if we look at this for parallel flow, this is going to be hot in minus cold in. So we have hot in minus cold in. That's at T1. So that's our delta T1. And then delta T2 for parallel flow, that's hot out minus cold out. And if we look at counterflow, delta T1, that's going to be THI or T hot minus T cold out. And then for T2, we have T hot out minus T cold in. Okay, so that's all I've done there. And then this natural log here, that's just taking the natural log of delta T1 divided by delta T2. So let's go back here. So for this, we're kind of working on our equation to find the overall heat transfer coefficient. So we're kind of plugging in right here. So we have delta T1, we have delta T2. That's what we did right here. Now we need the natural log for delta T1 and delta T2. Okay, so that's what I've done here. And again, we want to do this for both parallel flow and for counterflow. And then this part here is basically, I'm combining our pi times d times L, that heat transfer surface area. I'm combining that with delta T1 minus delta T2 divided by this natural log here. And so now all we have to do to solve for this heat transfer coefficient U is do U equals Q dot H. Remember, we're doing H, we're doing the hot fluid, divided by all of what we just had that we kind of simplified for right here. It's kind of a lot of things to keep track of again, but hopefully that made sense. So now we just kind of plug in for this and we can solve for the overall heat transfer coefficient for both the parallel flow and the counterflow. Okay, so now we're on the plotting portion of the lab. So this is for question 1. Question 1 is the uninsulated parallel and counterflow. So we're going to plot that temperature versus our axial position. So I'm just going to show you question 1 because question 2, that's just for the insulated configuration, but it's going to be, the same logic. So you want to have like one main kind of graph. That's where we're going to use the subplot command. And on the left here, we're going to have 4 graphs. That's going to be for parallel flow. And then on the right, it's going to be 4 graphs for counterflow. So that's what you see here. So I'll just go over this first graph here. And also make sure that your legends aren't blocking your curve. So I didn't do a good job here, but I would fix this one, and this one. You could either make the legend smaller, or you can even take out the border that we have here in the legend, and that could probably help as well. Or you could just move it, but I like being consistent with my legend placement. So anyways, subplot 4, 2, 1. So we have 4 rows and we have 2 columns. So that's where we have 4, 2. And that's going to stay the same for all of our plots here. But what's going to change is the last number here. So I have in this first graph right here, I have a comma 1. That's taking up this first placeholder right here. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8. So we're plotting x position on the x-axis, and then here we have TUPH, so we have the temperature for the uninsulated parallel flow for the hot fluid, and we're going to do that in red. So the hot fluid, that's always going to stay at 10 gallons per hour. But then the cold fluid, that's going to go from 2.5 gallons per hour up to 10 gallons per hour. So we're doing this for the first flow rate here. So while the hot fluid, that stays at 10 gallons per hour, this is for the configuration of hot fluid 10 gallons per hour, cold fluid 2.5 gallons per hour. So we're taking this first column here. So it goes from 2.5 to 5 to 7.5 to 10. Okay, so this is for the uninsulated part, but if we look at the next graph here, or this is for parallel flow, sorry, it's uninsulated parallel flow, and then graph 2, that's going to be uninsulated counterflow. So we have basically the same kind of thing here, but we're just changing our temperature to be counterflow instead of parallel flow. So you're going to make those necessary corrections. So again, we're going to be doing that same kind of logic this whole time here. So we have the first two graphs here. We have graphs 3 and 4. So I'm going to kind of go slowly. If you need to look at this, you shouldn't though. Graphs 5 and 6. And then 7 and 8. Alright. Okay, so that's figure 1. Alright, so now we have question 3 and question 4. Again, for question 2, I'm not going to go over that because it's, the exact same logic as question 1, except this time it's for the insulated configuration. So, question 3, uninsulated heat loss. So, we're plotting our delta Q, so hot minus cold, that heat transfer, against the cold fluid flow rate. So, the cold fluid flow rate, that went from 2.5 gallons per hour up to 10. And then delta Q, again, we already calculated that earlier. That was QH minus QC for parallel flow, and then QH minus QC for counterflow. And that was for uninsulated as well. Alright, so we plotted that. And then question 4, that's the insulated heat loss. So for that, we had to, we're looking at the overall heat transfer coefficient. So we have that here, and then our cold volumetric flow rate once again. And we're doing that for parallel and then counterflow. So pretty self-explanatory stuff, not too complicated there. I guess another thing here. I guess I'll accept it like this since I have it like this in the video, but really I would prefer if you had your units as a real fraction and not like this, but it's fine. I guess I'll let it go on the last one, huh? Okay, so that's it. We're done now. I hope you enjoyed it. Kind of an anticlimactic end to the semester here, but hopefully you enjoyed the class, and hopefully you learned some things that you didn't know, or you saw some fluids at least in person for the first 3 labs. Because that's all we had, but at least we got 3 labs in for the semester, and I hope you again learned something of value. And even though this isn't a Matlab class, hopefully you learned how to kind of process your data, and maybe learn something there as well. So anyways, I hope you enjoyed the semester, and hopefully I'll see some of you around campus once that opens, whenever that is. And good luck with all your other classes if you're still going to take finals for that, and good luck next semester. Alright, see you later.